Hello and welcome to this lecture. In this lecture, we will look at kubelet. Earlier we discussed that the kubelet is like the captain on the ship. They lead all activities on a ship. They're the ones responsible for doing all the paperwork necessary to become part of the cluster. They're the sole point of contact from the master ship. They load or unload containers on the ship as instructed by the scheduler on the master. They also send back reports at regular intervals on the status of the ship and the containers on them. The kubelet in the Kubernetes worker node registers the node with the Kubernetes cluster. When it receives instructions to load a container or a pod on the node, it requests the container runtime engine, which may be Docker, to pull the required image and run an instance. The kubelet then continues to monitor the state of the pod and containers in it and reports to the Kube API server on a timely basis. So how do you install the kubelet? If you use the kubeadmin tool to deploy your cluster, it does not automatically deploy the kubelet. Now that's the difference from the other components. You must always manually install the kubelet on your worker nodes. Download the installer, extract it, and run it as a service. You can view the running kubelet process and the effective options by listing the process on the worker node and searching for kubelet. We will look more into kubelets, how to configure kubelets, generate certificates, and finally how to TLS bootstrap kubelets later in this course. That's it for now. I will see you in the next lecture. Hello and welcome to this lecture. In this lecture, we will talk about kubeproxy. Within a Kubernetes cluster, every pod can reach every other pod. This is accomplished by deploying a pod networking solution to the cluster. A pod network is an internal virtual network that spans across all the nodes in the cluster to which all the pods connect to. Through this network, they're able to communicate with each other. There are many solutions available for deploying such a network. In this case, I have a web application deployed on the first node and a database application deployed on the second. The web app can reach the database simply by using the IP of the pod. But there is no guarantee that the IP of the database pod will always remain the same. If you have gone through the lecture on services, as discussed in the beginner's course, you must know that a better way for the web application to access the database is using a service. So we create a service to expose the database application across the cluster. The web application can now access the database using the name of the service, DB. The service also gets an IP address assigned to it. Whenever a pod tries to reach the service using its IP or name, it forwards the traffic to the backend pod, in this case, the database. But what is this service and how does it get an IP? Does the service join the same pod network? The service cannot join the pod network because the service is not an actual thing. It is not a container like pods, so it doesn't have any interfaces or an actively listening process. It is a virtual component that only lives in the Kubernetes memory. But then we also said that the service should be accessible across the cluster from any nodes. So how is that achieved? That's where kubeproxy comes in. Kubeproxy is a process that runs on each node in the Kubernetes cluster. Its job is to look for new services, and every time a new service is created, it creates the appropriate rules on each node to forward traffic to those services to the backend pods. One way it does this is using IP tables rules. In this case, it creates an IP tables rule on each node in the cluster to forward traffic heading to the IP of the service, which is 10.96.0.12, to the IP of the actual pod, which is 10.32.0.15. So that's how kubeproxy configures a service. We discuss a lot more about networking and services and kubeproxy and pod networking later in this course. Again, we have a large section just for networking. This is a high-level overview for now. We will now see how to install kubeproxy. Download the kubeproxy binary from the Kubernetes release page, extract it, and run it as a service. The kubeadm tool deploys kubeproxy as pods on each node, In fact, it is deployed as a daemon set, so a single pod is always deployed on each node in the cluster. Well, if you don't know about daemon set yet, don't worry. We have a lecture on that coming up in this course. We have now covered a high-level overview of the various components in the Kubernetes control plane. As mentioned, we will look at some of these in much more detail at various sections in this course. Well, that's it for this lecture. I will see you in the next section. Hello and welcome to this lecture on Kubernetes pods. Before we head into understanding pods, we would like to assume that the following have been set up already. At this point, we assume that the application is already developed and built into Docker images, and it is available on a Docker repository like Docker Hub, so Kubernetes can pull it down. We also assume that the Kubernetes cluster has already been set up and is working. This could be a single node setup or a multi-node setup, doesn't matter. All the services need to be in a running state. As we discussed before, with Kubernetes, our ultimate aim is to deploy our application in the form of containers on a set of machines that are configured as worker nodes in a cluster. However, Kubernetes does not deploy containers directly on the worker nodes. The containers are encapsulated into a Kubernetes object known as pods. A pod is a single instance of an application. A pod is the smallest object that you can create in Kubernetes. Here we see the simplest of simplest cases where you have a single node Kubernetes cluster with a single instance of your application running in a single Docker container encapsulated in a pod. What if the number of users accessing your application increase and you need to scale your application? You need to add additional instances of your web application to share the load. Now, where would you spin up additional instances? Do we bring up new container instance within the same pod? No. We create new pod altogether with a new instance of the same application. As you can see, we now have two instances of our web application running on two separate pods on the same Kubernetes system or node. What if the user base further increases and your current node has no sufficient capacity? Well, then you can always deploy additional pods on a new node in the cluster. You will have a new node added to the cluster to expand the cluster's physical capacity. So what I'm trying to illustrate in this slide is that pods usually have a one-to-one relationship with containers running your application. To scale up, you create new pods, and to scale down, you delete existing pod. You do not add additional containers to an existing pod to scale your application. Also, if you're wondering how we implement all of this and how we achieve load balancing between the containers, etc., we will get into all of that in a later lecture. For now, we are only trying to understand the basic concepts. We just said that pods usually have a one-to-one relationship with the containers, but are we restricted to having a single container in a single pod? No. A single pod can have multiple containers except for the fact that they're usually not multiple containers of the same kind. As we discussed in the previous slide, if our intention was to scale our application, then we would need to create additional pods. But sometimes you might have a scenario where you have a helper container that might be doing some kind of supporting task for our web application, such as processing a user-entered data, processing a file uploaded by the user, etc. And you want these helper containers to live alongside your application container. In that case, you can have both of these containers part of the same pod, so that when a new application container is created, the helper is also created, and when it dies, the helper also dies since they are part of the same pod. The two containers can also communicate with each other directly by referring to each other as local host, since they share the same network space. Plus, they can easily share the same storage space as well. If you still have doubts in this topic, I would understand if you did, because I did the first time I learned these concepts. We could take another shot at understanding pods from a different angle. Let's, for a moment, keep Kubernetes out of our discussion and talk about simple Docker containers. Let's assume we were developing a process or a script to deploy our application on a Docker host. Then we would first simply deploy our application using a simple docker run python app command, and the application runs fine and our users are able to access it. When the load increases, we deploy more instances of our application by running the docker run commands many more times. This works fine and we're all happy. Now, sometime in the future, our application is further developed, undergoes architectural changes, and grows and gets complex. We now have a new helper container that helps our web application by processing or fetching data from elsewhere. These helper containers maintain a one-to-one relationship with our application container and thus needs to communicate with the application containers directly and access data from those containers. For this, we need to maintain a map of what app and helper containers are connected to each other. We would need to establish network connectivity between these containers ourselves using links and custom networks. We would need to create shareable volumes and share it among the containers. We would need to maintain a map of that as well. And most importantly, we would need to monitor the state of the application container, and when it dies, manually kill the helper container as well, as it's no longer required. When a new container is deployed, we would need to deploy the new helper container as well. With pods, Kubernetes does all of this for us automatically. We just need to define what containers a pod consists of, and the containers in a pod by default will have access to the same storage, the same network namespace, and same fate, as in they will be created together and destroyed together. Even if our application didn't happen to be so complex and we could live with a single container, Kubernetes still requires you to create pods. But this is good in the long run, as your application is now equipped for architectural changes and scale in the future. However, also note that multi-containers pod are a rare use case, and we're going to stick to single containers per pod in this course.
Let us now look at how to deploy pods. Earlier, we learned about the kubectl run command. What this command really does is it deploys a Docker container by creating a pod. So it first creates a pod automatically and deploys an instance of the nginx Docker image. But where does it get the application image from? For that, you need to specify the image name using the image parameter. The application image, in this case the nginx image, is downloaded from the Docker Hub repository. Docker Hub, as we discussed, is a public repository where latest Docker images of various applications are stored. You could configure Kubernetes to pull the image from the public Docker Hub or a private repository within the organization. Now that we have a pod created, how do we see the list of pods available? The kubectl get pods command helps us see the list of pods in our cluster. In this case, we see the pod is in a container creating state and soon changes to a running state when it is actually running. Also, remember that we haven't really talked about the concepts on how a user can access the nginx web server. And so in the current state, we haven't made the web server accessible to external users. You can access it internally from the node, but for now, we will just see how to deploy a pod. And later, in a later lecture, once we learn about networking and services, we will get to know how to make this service accessible to end users. Well, that's it for this lecture. Head over to a demo, and I will see you in the next one.
Hello and welcome to this lecture. In this lecture, we will talk about creating a pod using a YAML-based configuration file. In the previous lecture, we learned about YAML files in general. Now we will learn how to develop YAML files specifically for Kubernetes. Kubernetes uses YAML files as inputs for the creation of objects such as pods, replicas, deployments, services, etc. All of these follow a similar structure. A Kubernetes definition file always contains 4 top-level fields: the API version, kind, metadata, and spec. These are the top-level or root-level properties. These are also required fields, so you must have them in your configuration file. Let us look at each one of them. The first one is the API version. This is the version of the Kubernetes API we are using to create the object. Depending on what we are trying to create, we must use the right API version. For now, since we are working on pods, we will set the API version as v1. Few other possible values for this field are apps/v1 beta, extensions/v1 beta, etc. We will see what these are for later in this course. Next is the kind. The kind refers to the type of object we are trying to create, which in this case happens to be a pod. So we will set it as pod. Some other possible values here could be replica set or deployment or service, which is what you see in the kind field in the table on the right. The next is metadata. The metadata is data about the object, like its name, labels, etc. As you can see, unlike the first two where you have specified a string value, this is in the form of a dictionary. So everything under metadata is intended to the right a little bit, and so names and labels are children of metadata. The number of spaces before the two properties, name and labels, doesn't matter, but they should be the same as they are siblings. In this case, labels has more spaces on the left than name, and so it is now a child of the name property instead of a sibling, which is incorrect. Also, the two properties must have more spaces than its parent, which is metadata, so that it's intended to the right a little bit. In this case, all three of them have the same number of spaces before them, and so they are all siblings, which is not correct. Under metadata, the name is a string value, so you can name your pod my app pod. And the labels is a dictionary, so labels is a dictionary within the metadata dictionary. And it can have any key and value pairs as you wish. For now, I have added a label app with the value my app. Similarly, you could add other labels as you see fit, which will help you identify these objects at a later point in time. Say, for example, there are hundreds of pods running a front-end application and hundreds of pods running a back-end application or a database. It will be difficult for you to group these pods once they are deployed. If you label them now as front-end, back-end, or database, you will be able to filter the pods based on this label at a later point in time. It's important to note that under metadata, you can only specify name or labels or anything else that Kubernetes expects to be under metadata. You cannot add any other property as you wish under this. However, under labels, you can have any kind of key or value pairs as you see fit. So it's important to understand what each of these parameters expect. So far, we have only mentioned the type and name of the object we need to create, which happens to be a pod with the name myAppPod. But we haven't really specified the container or image we need in the pod. The last section in the configuration file is the specification section, which is written as spec. Depending on the object we are going to create, this is where we would provide additional information to Kubernetes pertaining to that object. This is going to be different for different objects, so it's important to understand or refer to the documentation section to get the right format for each. Since we are only creating a pod with a single container in it, it is easy. Spec is a dictionary, so add a property under it called containers. Containers is a list or an array. The reason this property is a list is because the pods can have multiple containers within them, as we learned in the lecture earlier. In this case though, we will only add a single item in the list, since we plan to have only a single container in the pod. The dash right before the name indicates that this is the first item in the list. The item in the list is a dictionary, so add a name and image property. The value for image is nginx, which is the name of the Docker image in the Docker repository. Once the file is created, run the command kubectl create -f followed by the file name, which is pod definition.yaml, and Kubernetes creates the pod. So to summarize, remember the 4 top-level properties: API version, kind, metadata, and spec. Then start by adding values to those depending on the object you are going to create. Once we create the pod, how do you see it? Use the kubectl getPods command to see a list of pods available. In this case, it's just one. To see detailed information about the pod, run the kubectl describe pod command. This will tell you information about the pod, when it was created, what labels are assigned to it, what Docker containers are part of it, and the events associated with that pod. That's it for this lecture. We will now head over to a demo, and I will see you in the next lecture. In this demo, we're going to create a pod again, but this time, instead of making use of the kubectl run command, we are going to create it using a YAML definition file. So our goal is to create a YAML file with the pod specifications in it. Now, there are many ways to do it. You could just create one in any text editor. So if you're on Windows, you could just use Notepad, or if you're on Linux, as I am, just use a native editor like VI or Vim. An editor with support for YAML language would be very helpful in getting the syntax right. So instead of Notepad, a tool like Notepad++ in Windows or Vim in Linux would be better. Now I'll talk more about tips and tricks and other tools and IDEs that can help with this more in the upcoming lectures. For now, let's take with the very basic form of creating a YAML file using a VI editor on my Linux system. So here I am on my Linux terminal, and I'm going to make use of Vim text-based editor to create this pod definition file. So the name of the file I'm going to call as pod.yaml, and as seen in the lecture, we will start off with the 4 root level elements, or the root level properties that we saw, which are API version, kind, metadata, and spec. So we know that the value for API version for a pod is v1. The kind is pod with a capital P, so it is case sensitive, so that's important. And metadata is a dictionary, and it can have values where we define the name of the pod. So I'm going to use name as nginx, and we can have additional labels that we can specify under it. So labels again is also a dictionary, and it can have as many labels as you want under it. So we can specify a label which is a key value pair, such as app and nginx. And we can also add more labels like tier and set it to front end, anything that can help us group this particular pod. Next, we have to define the spec. So spec is also a dictionary. It has an object called containers. So before we move on to that, we have to make sure that we get the indentation right. For example, the app and tier are children of the labels property. So it has to be in the same kind of vertical line here. And similarly, under metadata, you have name and labels, which are the children of metadata. So they both have to be within the same vertical line. So you have to make sure that the spacing is correct. Typically it would be 2 spaces or a tab, but it is recommended not to use tabs. So always stick to 2 spaces and stick to that throughout. So the next thing that we're going to configure is the container. So a container is a list of objects. Now we first give it a name. Note that this is the name of the container within the pod, and there could be multiple containers and each can have a different name. So one container could be named app and another container could be named helper. Any name that makes sense to you. We're going to use the same name as that of the container image, so we will just name it nginx. And the second object that we're going to add here is the image name, which is the Docker Hub image name of the container that we're going to create. So the image name is again nginx. If you're using other registries than Docker Hub, then make sure to specify the full path to that image repository here. Now remember that we can add additional containers to the pod as well. So if you have to do that, we have to declare the secondary element to the list, which would be the second object in the list. So here I can, for example, add a busybox container using the busybox image, and that would be the second element of the array. So in this case, we're going to stick to one single container. So I'm going to just delete that. And I'm now going to hit escape :WQ to save this file, and we will just use the cat command to make sure that the file was created with the expected contents. So make sure the format is correct. So the name and labels are children of metadata, and you can see that they are on the same kind of vertical line. And similarly, labels have 2 children, which are the 2 labels, app and tier, and spec has a list, and we are defining it as a list with a hyphen followed by the objects. So we can make use of the kubectl create command or the kubectl apply command. So the create and apply command kind of works the same if you're creating a new object, right? You can either use create or you can use apply. It doesn't matter. And we pass in the file name using the -f option. And here we can see that the pod has been created. So let's check the status real quick. And you can see that it's in container creating state. And then when we check again, we see that it's in a running state. And as before, if you want to get more details about the pod, you can always run the kubectl describe command and specify the name of the pod. And you should get a much more in-depth information about the pod. Okay, so that's it for this demo. In the next section, we will learn some tips and tricks of developing YAML files easily using IDEs.
Before you head into a practice test, which follows this video, I wanted to spend a few minutes on walking you through the practice test portal. Following this lecture, you'll be taken to the labs. Click the Start button to load the lab. You must be accessing the practice test on a laptop or a desktop system, as you will require a keyboard to work hands-on. Allow some time for the labs to load. It usually loads in less than 30 seconds, and in rare scenarios, it might take a few minutes. So I request you to be patient when it takes a long time. Now, once the lab is loaded, you will find the quiz portal on the left, and it
Okay, so let's go. Hello and welcome to this lecture on Kubernetes controllers. My name is Mumshad Manambeth. In this lecture, we will discuss about Kubernetes controllers. Controllers are the brain behind Kubernetes. They are the processes that monitor Kubernetes objects and respond accordingly. In this lecture, we will discuss about one controller in particular, and that is the replication controller. So what is a replica and why do we need a replication controller? Let's go back to our first scenario where we had a single pod running our application. What if for some reason our application crashes and the pod fails? Users will no longer be able to access our application. To prevent users from losing access to our application, we would like to have more than one instance or pod running at the same time. That way, if one fails, we still have our application running on the other one. The replication controller helps us run multiple instances of a single pod in the Kubernetes cluster, thus providing high availability. So does that mean you can't use a replication controller if you plan to have a single pod? No. Even if you have a single pod, the replication controller can help by automatically bringing up a new pod when the existing one fails. Thus, the replication controller ensures that the specified number of pods are running at all times, even if it's just 1 or 100. Another reason we need replication controller is to create multiple pods to share the load across them. For example, in this simple scenario, we have a single pod serving a set of users. When the number of users increase, we deploy additional pod to balance the load across the two pods. If the demand further increases and if we were to run out of resources on the first node, we could deploy additional pods across the other nodes in the cluster. As you can see, the replication controller spans across multiple nodes in the cluster. It helps us balance the load across multiple pods on different nodes as well as scale our application when the demand increases. It's important to note that there are two similar terms, replication controller and replica set. Both have the same purpose, but they're not the same. Replication controller is the older technology that is being replaced by replica set. Replica set is the new recommended way to set up replication. However, whatever we discussed in the previous few slides remain applicable to both these technologies. There are minor differences in the way each works, and we will look at that in a bit. As such, we will try to stick to replica sets in all of our demos and implementations going forward. Let us now look at how we create a replication controller. As with the previous lecture, we start by creating a replication controller definition file. We will name it rc-definition.yaml. As with any Kubernetes definition file, we have 4 sections: the API version, kind, metadata, and spec. The API version is specific to what we are creating. In this case, replication controller is supported in Kubernetes API version v1. So we will set it as v1. The kind, as we know, is replication controller. Under metadata, we will add a name and we will call it myapp-rc, and we will also add a few labels, app and type, and assign values to them. So far, it has been very similar to how we created a pod in the previous section. The next is the most crucial part of the definition file, and that is the specification written as spec. For any Kubernetes definition file, the spec section defines what's inside the object we are creating. In this case, we note that the replication controller creates multiple instances of a pod. But what pod? We create a template section under spec to provide a pod template to be used by the replication controller to create replicas. Now, how do we define the pod template? It's not that hard because we have already done that in the previous exercise. Remember, we created a pod definition file in the previous exercise. We could reuse the contents of the file to populate the templates section. Move all the contents of the pod definition file into the template section of the replication controller, except for the first few lines, which are API version and kind. Remember, whatever we move must be under the template section, meaning they should be intended to the right and have more spaces before them than the template line itself. They should be children of the template section. Looking at our file now, we now have two metadata sections. One is for the replication controller and another for the pod, and we have two spec sections, one for each. We have nested two definition files together, the replication controller being the parent and the pod definition being the child. Now there is something still missing. We haven't mentioned how many replicas we need in the replication controller. For that, add another property to the spec called replicas and input the number of replicas you need under it. Remember that the template and replicas are direct children of spec sections, so they are siblings and must be on the same vertical line, which means having equal number of spaces before them. Once the file is ready, run the kubectl create command and input the file using the -f parameter. The replication controller is created. When the replication controller is created, it first creates the pods using the pod definition template, as many as required, which is 3 in this case. To view the list of created replication controllers, run the kubectl get replication controller command and you will see the replication controller listed. We can also see the desired number of replicas or pods, the current number of replicas, and how many of them are ready in the output. If you would like to see the pods that were created by the replication controller, run the kubectl get pods command and you will see 3 pods running. Note that all of them are starting with the name of the replication controller, which is myapp-rc, indicating that they are all created automatically by the replication controller. What we just saw was the replication controller. Let us now look at replica set. It is very similar to replication controller. As usual, first we have API version, kind, metadata, and spec. The API version, though, is a bit different. It is apps/v1, which is different from what we had before for replication controller, which was just v1. If you get this wrong, you are likely to get an error that looks like this. It would say no match for kind replica set, because the specified Kubernetes API version has no support for replica set. The kind would be replica set, and we add name and labels in the metadata. The specification section looks very similar to replication controller. It has a template section where we provide pod definition as before. So I'm going to copy contents over from pod definition file, and we have number of replicas, which is set to 3. However, there is one major difference between replication controller and replica set. Replica set requires a selector definition. The selector section helps the replica set identify what pods fall under it. But why would you have to specify what pods fall under it if you have provided the contents of the pod definition file itself in the template? It's because replica set can also manage pods that were not created as part of the replica set creation. Say, for example, there were pods created before the creation of the replica set that matched labels specified in the selector. The replica set will also take those pods into consideration when creating the replicas. I will elaborate this in the next slide. But before we get into that, I would like to mention that the selector is one of the major differences between replication controller and replica set. The selector is not a required field in case of a replication controller, but it is still available. When you skip it, as we did in the previous slide, it assumes it to be the same as the labels provided in the pod definition file. In case of replica set, a user input is required for this property, and it has to be written in the form of match labels as shown here. The match labels selector simply matches the labels specified under it to the labels on the pod. the replica set selector also provides many other options for matching labels that were not available in a replication controller. And as always, to create a replica set, run the kubectl create command providing the definition file as input. And to see the created replicas, run the kubectl get replica set command. To get list of pods, simply run the kubecontrol get pods command. So what is the deal with labels and selectors? Why do we label our pods and objects in Kubernetes? Let us look at a simple scenario. Say we deployed 3 instances of our front-end web application as 3 pods. We would like to create a replication controller or replica set to ensure that we have 3 active pods at any time. And yes, that is one of the use cases of replica sets. You can use it to monitor existing pods if you have them already created, as it is in this example. In case they were not created, the replica set will create them for you. The role of the replica set is to monitor the pods and if any of them were to fail, deploy new ones. The replica set is in fact a process that monitors the pods. Now, how does the replica set know what pods to monitor? There could be hundreds of other pods in the cluster running different applications. This is where labeling our pods during creation comes in handy. We could now provide these labels as a filter for replica set. Under the selector section, we use the match labels filter and provide the same label that we used while creating the pods. This way, the replica set knows which pods to monitor. The same concept of labels and selectors is used in many other places throughout Kubernetes. Now, let me ask you a question along the same lines. In the replica set specification section, we learned that there are 3 sections: template, replicas, and the selector. We need 3 replicas, and we have updated our selector based on our discussion in the previous slide. Say, for instance, we have the same scenario as in the previous slide, where we have 3 existing pods that were created already, and we need to create a replica set to monitor the pods to ensure there are a minimum of 3 running at all times. When the replication controller is created, it is not going to deploy a new instance of pod as 3 of them with matching labels are already created. In that case, do we really need to provide a template section in the replica set specification, since we are not expecting the replica set to create a new pod on deployment? Yes, we do, because in case one of the pods were to fail in the future, the replica set needs to create a new one to maintain the desired number of pods. And for the replica set to create a new pod, the template definition section is required. Let's now look at how we scale the replica set. Say we started with 3 replicas, and in the future we decided to scale to 6. How do we update our replica set to scale to 6 replicas? Well, there are multiple ways to do it. The first is to update the number of replicas in the definition file to 6. Then run the kubectl replace command to specify the same file using the -f parameter, and that will update the replica set to have 6 replicas. The second way to do it is to run the kubecontrol scale command, use the replicas parameter to provide the new number of replicas and specify the same file as input. You may either input the definition file or provide the replica set name in the type name format. However, remember that using the file name as input will not result in the number of replicas being updated automatically in the file. In other words, the number of replicas in the replica set definition file will still be 3, even though you scaled your replica set to have 6 replicas using the kubecontrol scale command and the file as input. There are also options available for automatically scaling the replica set based on load, but that is an advanced topic and we will discuss it at a later time. Let us now review the commands real quick. The kubectl create command, as we know, is used to create a replica set, or basically any object in Kubernetes, depending on the file we are providing as input. You must provide the input file using the -f parameter. Use the kubectl get command to see list of replica sets created. Use the kubectl delete replica set command followed by the name of the replica set to delete the replica set. And then we have the kubectl replace command to replace or update the replica set, and also the kubectl scale command to scale replica set simply from the command line without having to modify the file. That's it for this lecture. Hello and welcome to this lecture. My name is Mumshad Manambeth. In this lecture, we will discuss about Kubernetes deployments. For a minute, let us forget about pods and replica sets and other Kubernetes concepts and talk about how you might want to deploy your application in a production environment. Say, for example, you have a web server that needs to be deployed in a production environment. You need not one, but many such instances of the web server running for obvious reasons. Secondly, whenever newer versions of application builds become available on the Docker registry, you would like to upgrade your Docker instances seamlessly. However, when you upgrade your instances, you do not want to upgrade all of them at once as we just did. This may impact users accessing our application, so you might want to upgrade them one after the other. And that kind of upgrade is known as rolling updates. Suppose one of the upgrades you performed resulted in an unexpected error and you're asked to undo the recent change. You would like to be able to roll back the changes that were recently carried out. Finally, say for example, you would like to make multiple changes to your environment, such as upgrading the underlying web server versions, as well as scaling your environment and also modifying the resource allocations, etc. You do not want to apply each change immediately after the command is run. Instead, you would like to apply a pause to your environment, make the changes, and then resume so that all the changes are rolled out together. All of these capabilities are available with the Kubernetes deployments. So far in this course, we discussed about pods, which deploy single instances of our application, such as the web application in this case. Each container is encapsulated in pods. Multiple such pods are deployed using replication controllers or replica sets. And then comes deployment, which is a Kubernetes object that comes higher in the hierarchy. The deployment provides us with the capability to upgrade the underlying instances seamlessly using rolling updates, undo changes, and pause and resume changes as required. So how do we create a deployment? As with the previous components, we first create a deployment definition file. The contents of the deployment definition file are exactly similar to the replica set definition file, except for the kind, which is now going to be deployment. If we walk through the contents of the file, it has an API version, which is apps/v1, metadata, which has name and labels, and a spec that has template, replicas, and selector. The template has a pod definition inside it. Once the file is ready, run the kubectl create command and specify the deployment definition file. Then run the kubectl get deployments command to see the newly created deployment. The deployment automatically creates a replica set. So if you run the kubectl get replica set command, you will be able to see a new replica set in the name of the deployment. The replica sets ultimately create pods. So if you run the kubectl get pods command, you will be able to see the pods with the name of the deployment and the replica set. So far, there hasn't been much of a difference between replica set and deployments, except for the fact that deployment created a new Kubernetes object called deployments. We will see how to take advantage of the deployment using the use cases we discussed in the previous slide in the upcoming lectures. And one more note before we end this lecture: to see all the created objects at once, run the kube control get all command. And in this case, we can see that the deployment was created, and then we have the replica set followed by 3. Hello and welcome to this lecture. My name is Mumshad Manambet and we are learning Kubernetes for beginners. In this lecture, we will discuss about Kubernetes services. Kubernetes services enable communication between various components within and outside of the application. Kubernetes services helps us connect applications together with other applications or users. For example, our application has groups of pods running various sections, such as a group for serving a front-end load to users, another group for running back-end processes, and a third group connecting to an external data source. It is services that enable connectivity between these groups of pods. Services enable the front-end application to be made available to end users. It helps communication between back-end and front-end pods and helps in establishing connectivity to an external data source. Thus, services enable loose coupling between microservices in our application. Let's take a look at one use case of services. So far, we talked about how pods communicate with each other through internal networking. Let's look at some other aspects of networking in this lecture. Let's start with external communication. So we deployed our pod having a web application running on it. How do we, as an external user, access the web page? First of all, let's look at the existing setup. The Kubernetes node has an IP address, and that is 192.168.1.2. My laptop is on the same network as well, so it has an IP address 192.168.1.10. The internal pod network is in the range 10.244.0.0, and the pod has an IP 10.244.0.2. Clearly, I cannot ping or access the pod at address 10.244.0.2 as it's in a separate network. So what are the options to see the web page? First, if we were to SSH into the Kubernetes node at 192.168.1.2, from the node we would be able to access the pod's web page by doing a curl, or if the node has a GUI, we would fire up a browser and see the web page in a browser following the address http 10.244.0.2. But this is from inside the Kubernetes node, and that's not what I really want. I want to be able to access the web server from my own laptop without having to SSH into the node and simply by accessing the IP of the Kubernetes node. So we need something in the middle to help us map requests to the node from our laptop through the node to the pod running the web container. This is where the Kubernetes service comes into play. The Kubernetes service is an object just like pods, replica set, or deployments that we worked with before. One of its use cases is to listen to a port on the node and forward requests on that port to a port on the pod running the web application. This type of service is known as a node port service because the service listens to a port on the node and forward requests to the pods. There are other kinds of services available, which we will now discuss. The first one is what we discussed already, node port, where the service makes an internal pod accessible on a port on the node. The second is cluster IP, and in this case, the service creates a virtual IP inside the cluster to enable communication between different services, such as a set of front-end servers to a set of back-end servers. The third type is a load balancer, where it provisions a load balancer for our application in supported cloud providers. A good example of that would be to distribute load across the different web servers in your front-end tier. We will now look at each of these in a bit more detail along with some demos. In this lecture, we will discuss about the Node Port Kubernetes service. Getting back to Node Port, a few slides back, we discussed about external access to the application. We said that a service can help us by mapping a port on the node to a port on the pod. Let's take a closer look at the service. If you look at it, there are 3 ports involved. The port on the pod where the actual web server is running is 80, and it is referred to as the target port because that is where the service forwards the request to. The second port is the port on the service itself. It is simply referred to as the port. Remember, these terms are from the viewpoint of the service. The service is in fact like a virtual server inside the node. Inside the cluster, it has its own IP address, and that IP address is called the cluster IP of the service. And finally, we have the port on the node itself, which we use to access the web server externally, and that is known as the node port. As you can see, it is set to 30,008. That is because node ports can only be in a valid range, which by default is from 30,000 to 32,767. Let's now look at how to create the service. Just like how we created a deployment, replica set, or pod in the past, we will use a definition file to create a service. The high-level structure of the file remains the same. As before, we have the API version, kind, metadata, and spec sections. The API version is going to be v1. The kind is, of course, service. The metadata will have a name, and that will be the name of the service. It can have labels, but we don't need that for now. Next, we have spec, and as always, this is the most crucial part of the file, as this is where we will be defining the actual services, and this is the part of a definition file that differs between different objects. In the spec section of a service, we have type and ports. The type refers to the type of service we are creating. As discussed before, it could be cluster IP, node port, or load balancer. In this case, since we are creating a node port, we will set it as node port. The next part of a spec is ports. This is where we input information regarding what we discussed on the left side of the screen. The first type of port is the target port, which we will set to 80. The next one is simply port, which is the port on the service object, and we will set that to 80 as well. The third is node port, which we will set to 30,008 or any number in the valid range. Remember that out of these, the only mandatory field is port. If you don't provide a target port, it is assumed to be the same as port, and if you don't provide a node port, a free port in the valid range between 30,000 and 32,767 is automatically allocated. Also note that ports is an array, so note the dash under the port section that indicate the first element in the array. You can have multiple such port mappings within a single service. So we have all the information in, but something is really missing. There is nothing here in the definition file that connects the service to the pod. We have simply specified the target port, but we didn't mention the target port on which pod. There could be hundreds of other pods with web services running on port 80. So how do we do that? As we did with the replica sets previously, and a technique that you will see very often in Kubernetes, we will use labels and selectors to link these together. We know that the pod was created with a label. We need to bring that label into the service definition file. So we have a new property in the specs section, and that is called selector, just like in a replica set and deployment definition files. Under the selector, provide a list of labels to identify the pod. For this, refer to the pod definition file used to create the pod. Pull the labels from the pod definition file and place it under the selector section. This links the service to the pod. Once done, create the service using the kubectl create command and input the service definition file, and there you have the service created. To see the created service, run the kubectl get services command that lists the service, the cluster IP, and the mapped ports. The type is node port as we created, and the port on the node is set to 30008 because that's the port that we specified in the definition file. We can now use this port to access the web service using curl or a web browser. So curl to 192.168.1.2, which is the IP of the node, and then I use the port 30008 to access the web server. So far we talked about a service mapped to a single pod, but that's not the case all the time. What do you do when you have multiple pods? In a production environment, you have multiple instances of your web application running for high availability and load balancing purposes. In this case, we have multiple similar pods running our web application. They all have the same labels with a key app and set to a value of my app. The same label is used as a selector during the creation of the service. So when the service is created, it looks for a matching pod with the label and finds 3 of them. The service then automatically selects all the 3 pods as endpoints to forward the external request coming from the user. You don't have to do any additional configuration to make this happen. And if you're wondering what algorithm it uses to balance the load across the 3 different pods, it uses a random algorithm. Thus, the service acts as a built-in load balancer to distribute load across different pods. And finally, let's look at what happens when the pods are distributed across multiple nodes. In this case, we have the web application on pods on separate nodes in the cluster. When we create a service, without us having to do any additional configuration, Kubernetes automatically creates a service that spans across all the nodes in the cluster and maps the target port to the same node port on all the nodes in the cluster. This way, you can access your application using the IP of any node in the cluster and using the same port number, which in this case is 30008. As you can see, using the IP of any of these nodes, and I'm trying to curl to the same port, and the same port is made available on all the nodes part of the cluster. To summarize, in any case, whether it be a single pod on a single node, multiple pods on a single node, or multiple pods on multiple nodes, the service is created exactly the same without you having to do any additional steps during the service creation. When pods are removed or added, the service is automatically updated, making it highly flexible and adaptive. Once created, you won't typically have to make any additional configuration changes. That's it for this lecture. Head over to the demo and I will see you in the next lecture.